I know that's really the problem.
Just to complete what Dr. Larsen said, experimentalists could use fine rules too. I have some experimentalist friends are using it and working with it. So even for, it could be also interesting for the experimentalists. So yesterday, Johan and Olivier talked about Monte Carlo tools and MGraph, and how to use those tools, this tool to simulate physics at colliders. And here, the topic is a bit different, because we talk about fine rules, which is a tools which allow to feed MGraph with models, new physics models, and then you will be able to simulate any theory of your dream, roughly. Maybe not all of them, but let's say a large class of them. And we'll try to show you how to use fine rules to implement through fine rules directly to MGraph any new physics model. So the outline of the talk is divided in several parts. So first I will present fine rules within its context of all of these Monte Carlo chain. On the second and third part I will use it on a real example, because how to learn how to use the tools is just to use it. So I will choose a theory, which is supersymmetric QCD. I'm a SUSY guy, so I'm a bit biased. So I've chosen the SUSY theory. And I will implement this step by step on the slide, so that you can really see how it works. And then you can, starting from the slide, implement anything you want. And that will be your task during the tutorial sessions of tomorrow and after tomorrow. So this is the second and third part. I will probably start today and continue tomorrow. And for the fourth and fifth part, I will show you some more advanced techniques that can be used to fine rules, because fine rules has now many, many more tools. Let's say satellite tools that you could use to facilitate your life in the robotic models. So how to present the context? First of all, let's say one of the goals of the LHC is just to decide which new physics theory is the correct one. There is a very strong assumption here that there is new physics, of course. Maybe the LHC would just be, let's say we were talking about the rings yesterday with the other lecturers, so maybe the LHC is just the one ring, the one which will rule them out. And to do that, we need two things. Data, and those are there. Now, we'll not talk much about data today, but we need them on the one hand, and on the other hand, we need predictions, theoretical predictions, and then we need to confront them, and we can draw conclusions. This theory is correct, this one is not, etc., etc. And for those predictions, we need basically the backgrounds, and this is known, and the BSM signals. And this is not that known. It is known for, let's say, investigated models. But maybe new models will appear regarding the discoveries at the LHC. And for those, we'll have to do the phenomenology, let's say, on the fly. And that's how finance comes into the game. To be able to do this phenomenology quickly and efficiently to be able to select the correct or incorrect theories. If you take, for instance, the picture of the W plus 2 jet signal at CDF, I think now there are more than hundreds of theory papers trying to explain this. If you have some new signal at LHC, many theories will appear, and you have to test all of them. And to do that, you need to be quick in, let's say, in computing time, implementing the models in the tools. And that's the scope of finance, actually. So just to remind you, those theoretical predictions here, you have two options. You can take a pen and paper and do it. It's not nice. I mean, it's a good exercise. It's good to do that once in your life. That's the thing I'm repeating to my students. Do the thing by hand once in your life and then use the automatic tools. So that you know what's inside the black box. And by hand, of course, you can do 2 to 2 processes. That's easy. 2 to 3, that's doable. 2 to 4, sometimes, but not more. While with the automated tools, you can, I think Johan showed me an example of 2 to 14, right? And by hand, I don't even want to try to do that myself. Maybe if you are courageous, you can do that, but personally, I won't do that. And also with the tools, you can interface them to simulate a full collision environment using photon showing, detector simulation, etc., etc. While with handmade calculation, it's a bit more complicated, right? So this is a picture of what could happen at JHC. So first of all, some hexes has to be established. This is hard. I will not say the opposite. I'm not an experimentalist, but this is a purely experimental task, and this is very hard. Because you need really to understand the backgrounds, the detectors, etc., etc. And we are sure that what you observe is not any fancy effect of your detector or some background which was not considered. Then you can say that's new physics. And to do that task, Monte Carlo generators will be used to generate those backgrounds and signals. And when the access is confined, then it's when theory comes into the game, because there will be a lot of model building activities, both following bottom-up and top-down approaches. So the bottom-up approach, we start with the data, we try to cook something which will produce the data, and then we have something which works, we go to other signature, and so we are really we are really constructing the theory from the data to the model. While the top-down approach is different, we say we have supersymmetry. I'm a Suzy guy. And so we assume supersymmetry, and we see how supersymmetry could reproduce the data. So one is going from the theory to the data, and the approach is going from the data to the theory. And we need both, of course. One is not enough, especially if new physics is tricky. We don't know in advance. And once this is done, when the new physics is, when all those model building activities, we will choose the correct theory, then all the parameters will have to be measured. And to do that, we probably need some more than Monte Carlo tools like precision predictions. And now, for a couple of years, we have the next to leading order Monte Carlo tools. They could talk about that. And those are very important for those precision predictions and to extract the parameters from the data. And at the same time, the theoretical predictions become more and more precise. The experimental analysis will become more and more sophisticated. Because with time going, the detectors are much well understood, and also the new physics is better understood, so we know how to do the analysis. And if you look carefully to all of those points, the word Monte Carlo generators is appearing everywhere. Okay, not here, but it's appearing there also, of course. So they really play a key role. And so let's start with those Monte Carlo tools and try to think about how new physics will be and is currently investigated within those tools. And this is the pictures, let's say, before finals. I will show you what it becomes. And we have really separated blocks. So first of all, to investigate new physics, we need a good idea. Supersymmetry. And once we have the good idea, we need to sit down on a desk, take a pen, paper, and really try to construct a theory. Do some leading order or loop calculations to show the basic features of our new theory. Also check that all electroweak, low energy constraints, maybe dark matter constraints are fulfilled. And then you can write a couple of implications from that. And at some point, the theory guy will just say, I'm stopping here. I'm happy, I've constructed something which is okay regarding the current data. a couple of months later, a phenomenologist can say, oh, that model looks cool. Maybe we could try to see what's going on at colliders for that model. He will take the theory there, extract the Feynman rules, plug them into the Monte Carlo event generators, so that he could automatically calculate matrix elements. Or a couple of years ago, not automatically. Before MGraph, for instance, you have to do that by hand, in PTR, for instance. Switch on some pattern showing or randomization algorithms, and finally, maybe if it's really motivated to do some generic detector simulation. When this is done, you can say, okay, this theory, this model could be observed at the LHC, at Teraton, or anywhere with that probability, etc. I can write out some implications. And then the story stops, and you need to wait a couple of years more. And one essential friend of that guy can say, well, your theory is really cool. We should test it in reality, because the real life is there. It's not there. Come on. The real life is the data. It's not the theoretical ideas. Okay, theory is also a part of the real life. I mean, what's going on is already there with the data. That's the tool. Those are the models. And so we will take this cool model, plug it into its own experimental framework, for instance, CMSSW or Athena or CMS and Atlas. I don't know the names of the others. And then we will do the same exercise, computing matrix elements, switching on patternization, etc., and use this time a realistic detector simulation, a huge simulation of that detector. And then they can compare the data and say, okay, I will write down my publication stating that this theory is ruled out. May happen, or this theory could work after some refinement. And then the good thing would be to restart there, to refine the theory. But there is no error here. So usually the story stops there. So that was the picture before finals. And that's the thing we are trying, the message we are trying to show is to change this a bit. Let me show you by what in a moment. So now, what about those new physics theories and how to implement them into the tools? Well, there are many, many new physics theories. Hundreds, maybe thousands. I'm not counting them. And as soon as there is a new access somewhere, you can bet on 300 or 400 new physics theories in 3 months. This number is quite reasonable. And all of those theories are based on very different ideas. So it's not that easy to go from one theory to the next one, etc. And it's evolving. New discoveries, new theories, and so on and so forth. So it's not fixed. It's really a dynamical field. And for all of those theories, we would like to implement them in the tools. How does it work? So first of all, what's a model? What's a new physics model? It's a bunch of particles, a bunch of parameters, and some interactions, or finite. So that's how to, let's say, the skeleton of the theory is this. And you need to give those information to the Monte Carlo tools. So first of all, you need to derive by hand the Feynman rules. Usually you take your Lagrangian and you extract them. It's a very easy quantum theory exercise. I'm asking that to my master students, and they're doing it very well. It's easy. You have a recipe, you apply it. But it's not all the time easy. Take the MSSM, which is 105 free parameters. The most general one. You have something like 10,000 Feynman rules. Doing something easy but 10,000 times, I guess the probability of making a mistake is 1, right? You will probably be correct for the first 10 vertices, and then you start to be a bit tired and do some crazy stuff. But let's assume you can derive by hand all of those 10,000 Feynman rules. Then you need to translate them in a programming language, because those Monte Carlo tools are Fortran, C++, Python codes. So you need to translate the Feynman rules into their language. And again, you need to it's easy from principle, but you need to do that 10,000 times. Then you can make mistakes, of course. And if you want to do several tools, you need to do that several times. And one is Python, the other one is C++, and the third one is Fortran. So you cannot reuse what you're doing. You need to really redo it. So it's a bit of pain. And of course, if you want to test 2 models, you need to do that 2 times. More and more. So basically, all the work will be done and redone. It's a good exercise for reinventing the wheel. And that's not good. Because it's better to have this automatized, to do it once for all, and then the computer is doing it for you. At least once your algorithm is strong enough, you're sure there's no mistake at the end. And of course, you need to think, because not all the tools allow for any Lorentz structure or any Euler structure. So maybe you need to reject some of the vertices of your model. If you have color sextet, for instance, only for a few months, those guys are available in Tue1 MGraph. Before, you just need to remove them from your model because you cannot test them, or not easy. So it's also good to have some tools taking your Lagrangian and rejecting all the things which cannot be tested or implemented. And associated to that is the validation procedure. This is a thing. You need to do that at each step. And even during the validation procedure, it's better not to make any mistake. And how to validate something you're doing by hand? Usually you take some existing results, either analytical or numerical, and you check it works. For instance, if you have a new physics theory, any new physics theory should reproduce a certain model in some limit. So you take that limit from your theory and you check E plus minus to E plus minus. And you check it works. That's the kind of comparison you could do. And of course, for many models, the set of available results is very restricted. So you have not that information. So for the validation, you can just say at some point, I'm stopping here. My theory is partially validated, but I don't know for the rest. I have nothing to compare with. And then sometimes you will just say, since it's not validated, I will keep it for me. And then the distribution of all the implementation is a bit chaotic. And there are exceptions, of course. And the good exception is the MSSM, the associative theory again. And this model is very popular, and it has been widely tested by taking several tools, the MSSM implementation with all of those tools, and people, including Professor Agiwara a couple of years ago, have really confronted the result of those various tools and said, okay, this is wrong, let's change this, this is correct. And at the end of the story, they have tested like hundreds of processes, and all the tools, I think there were 4 or 5 tools, I don't remember exactly, but all of them were giving the same results. And I think you have done everything by hand, right? At that time? And you were faster than the tools, but I think But except for that model, for all the rest, such comparisons were not existing before. And of course, many people, especially at the experimental level, are taking, for example, PTR, adding something by hand, cooking something, and then using this hack version for the analysis. And a couple of years later, this guy is not in that experiment anymore, but switched to another one, and nobody remembers what he has done. So the traceability issue is really important. If you do something in one experiment, it could be good to take that model and test it in the second experiment 25 years later. So documentation, traceability is very, very important. So the conclusion of this is we really need an efficient framework to develop the model, to implement them into tools and validate them, and then to test the model against the data. And as a bonus of all of this, because this is theory, this is phenomenology, and this is experiment, if you have a good framework, all the guys have their place there. The experimentalists, the theorists, the phenomenologists, and we will really enhance communication between the different people in our field. And that's the idea. And this is the result, what we propose with finals. First of all, very important, all the arrows are going in both directions, up and down. You still start from your theoretical idea. You write down the Lagrangian. So this is your theory. You feed finals with this, and finals then feeds all the matrix and range generators here. And you don't have to do that yourself. You just then when you are there, you can switch on some part on sharing, some organization, and maybe possibly some dynamic detector simulation, and you can do some phenomenology. And as a result of your logical investigation, you can say that model or that simulation is very interesting, and then you can instead replace this generic detector simulation by a realistic one, and the experimentalist can then come to the data. And if something is very bad, we can go up and go up and go up, change something here, go down, go down, go down, go down, and do this kind of very nice loop. This is the idea, the final space framework proposed years ago. And what you will do here, you will learn those steps here first. So the final tutorial is divided into 2 sessions. So the first session will be here, and the second session will be here, and you will stop at the idealization level. I think Olivier will do something with generic detector maybe. Yes, no? Okay. So we will stop here. But you were showing yesterday how to go there, right?
The mixed engineering detector yesterday normally.
Normally? Okay.
So
So you're supposed to be inside here. So for theorists, usually we are stopping here. Some of them are going to there, but that's some exceptions when we are really strong in theory and experimental collaboration. But I don't know many of those. Maybe you know more than me. But it's quite rare. But at the time of DLHC, that's very possible. In CMS, there are a couple of theories inside the collaboration, right? So maybe this will become more and more frequent in the next years. So what the finals approach is just to say, okay, in the Monte Carlo implementations, we have the final rules. But in the final rules, there's not that much information, or too much information. If you change a copy, you need to change probably like 100 final rules. So it's very hard to change something called the final rules. While if you had a Lagrangian, which is more compact, which contains everything. So the idea is to say, let's start from the physics. And the physics is a Lagrangian. If I'm showing you a Lagrangian, you're able to say, the field constant of my theory is this. The parameters of my theory is that. And the interaction is this. So the Lagrangian is everything. You have all the information there. And so that's the only way to uniquely define every single model. Whatever is the tool you want to use, and whatever is the convention. The Lagrangian is an equation. It's not a C++ code. And if you want to change your model, you just change something in your Lagrangian. Switch off a term, add a new term, change a parameter, etc. So that's very easy to do that at the Lagrangian level. But if you want to change at the Monte Carlo level, adding a new particle, you need to add all the interactions consistently. That's a bit complicated. So what we want to do with finals is to have a general environment to implement any Lagrangian-based model. And then from that Lagrangian to interface several Monte Carlo generators. By having several of them, you can compare them because they are computing the same thing using different ways. So if the results are the same, you're pretty sure you have done the thing correctly. And we want also a framework which is easy to validate and maintain. We don't want something complicated. We want something that anyone can use in 5 minutes. Maybe at the end of those lectures, we'll be able to use finals, all of them, hopefully. And at the end of the game, if you remember this chain, we want to have the data here, so the experiment. So we really want to integrate this framework, inject into the software. So that's the aims. And just for some nice pictures from one collaborator, that's a link. This tree, this huge tree, is your Lagrangian. It's your theory. All your theory is there. And this poor guy wants to extract the family rules to feed his matrix dimensionator. And this is the tool he has. You know how to do it. It's very easy. You need to just to get some slice of the tree and get this. But with this tool, this can take quite a long time. While finals, this is this huge machine taking up you have here some information about the gauge theory and the content, and you get to feed all these small pieces. And when you have all of those pieces, you can feed MGraph or Sherpa or finance or any other. So this is how it works. You're going from prehistory to the future. So in one slide, this is finals. So this year I've already said when you're in times today, is to develop the models and go through the data basically, but you can start at the philological level. I would be happy to start here. I'm a theory, I'm not an experimentalist. And finals is based on Mathematica because you want something flexible. And what is finals doing in one sentence is exactly this. It derives final rules from a Lagrangian. Your Lagrangian can be 50 vertices, can be 10,000 vertices. It works the same. Sometimes you just need to take your time and get a coffee. Sometimes, if your Lagrangian is a bit more complicated, you can have a coffee and a meal. In principle, it's going quite fast. And there are, of course, some restrictions. We need a local theory, Lorentz and gauge environment. That's it. So the restrictions are, let's say, reasonable. And of course, finals is not supporting any field. For instance, if you want to build a theory for 5 hard fields, as we were discussing yesterday, this is not supported. Only scalar particles, fermions, vectors, and their associated ghosts, tensor fields, spin 2, and and superfields are supported. And in development, we have the spin 3 half, the Radical spin 3. So, and we probably stop at spin 2, not go higher. At least not now. And then finally is coming with several interfaces which will export those information to different Monte Carlo generators. And this is the scheme. We start, this is a model that we can really divide in 4 blocks. The parameters, the gauge groups, the particles, and the Lagrangian. We feed finals those information, and we extract the final rules. Then there's a nice features for theorists which want to write down a theory paper. They can have all their equation for free, just pressing a button. That's how we are starting to get lazy. Then, okay, now we are more interested in phenomenology and in configuration with data. We will not follow that arrows, but just follow the vertical one. And we will take those finals and feed one of those translation interfaces, and then we have for 3 models for all of those codes here. So we have MGraph 4 and 5 in the middle. That's, of course, because it's MGraph school. But if you prefer another of those guys, you can switch the boxes, no problem with me. Maybe there's a problem for the guys there. You should ask them. But at least for me, it's fine. And when you are there, you can switch on some algorithms for pattern training, analyzation, defector simulation, and do some analysis. And the analysis can be done here at that level, pattern level, or here at the other level, or there at the detector level. You could do whatever you want. And this is the picture. And now the only task, since everything is just pressing a button, but this yellow box here, we need to feed finals with some information. Once information is in finals, you can just press a button and do the physics there. So basically what we have to do is to implement the model and do the physics. And in between, all which is computing related, this comes for free. So instead of spending 90% of our time doing computing, implementing stuff, we can spend 90% of our time on physics, which we are physicists, not informatics.
This translation interface is different for different dimensions?
Yeah, because as I was saying in this, okay, I don't remember which slide, but all these codes here have different requirements. So sometimes when you take a Lagrangian, some structures are not supported by one code, so you need to clean it with your Lagrangian first. And also, for MGraph 5 is a Python program, Calcat is a C1, sorry. Blizzard is Fortran 2003 and OCaml. So you need to translate your finals in the correct language. And recently we have proposed the UFO, which is the standard model format for MGraph. And UFO stands for Universal Finals Output. It's universal in a sense, it's not tied to any of them. It's just a Python module you can link to any code. So that's the idea. Not to let's say in a quite near future, we can hope for having just the UFO and all the codes are just taking the UFO and extracting the information you need from the UFO file. Today, this is a dream. Tomorrow, I don't know. I have some idea about it, but I am not allowed to talk here. Because I don't want to offend. It's video recorded, I don't want to offend. Then we keep that for me. So why Mathematica? Because Mathematica is expensive, right? That's not Mathematica. I think all institutes have Mathematica licenses here, right? But okay, if you want to use finals on your own laptop, this is expensive. But this is a great tool. Because first of all, it's very flexible to do symbolic manipulations. If you have symbols and you want analytical expressions and you want to play with it, it's very easy with Mathematica. And that's allowed to implement routine to check if your Lagrangian is correct. A Lagrangian must be a mission. This is very easy to do in Mathematica. And also, there are built-in features in Mathematica, like matrix diagonalization. So from your Lagrangian, you can extract your mass spectrum and diagonalize it, at least numerically. Analytically, it depends on the size of your mass matrices, of course. But numerically, you can always do it. So this is very, very nice inside there, that we don't have to implement it by hand. And of course, if you are a theorist and you really want to write down a small program calculating all the parameters of your model, you can write Mathematica, even a model spectrum calculator. And this is not very complicated. So that's the good thing, is that you can always add functions and routines to code yourself. And that's one of the key choice. That's what we have chosen Mathematica. About the interfaces, the aim, we don't care about the codes lying behind. They can have different philosophy, architecture, whatever. The translation interface is just there to translate, as the name is there. I'm taking an equation and I have some files, as you know. And this maximizes the probability to have at least one code per model. And if you have one code working for each model, you can test that model. So this is the theory about finals, if we can call that theory, of course. And now let's go to a practical example and try this. I will not say that SUSY QCD is very simple, but it's simple enough, and it's good to illustrate all the features of how we implement models in finals. So what is SUSY QCD? In fact, I will not really talk about SUSY QCD. I will talk about, say, a restricted SUSY QCD because I want to simplify the model. Because I don't need 12 squads for the scope of the example. So it's enough to have 3 generations of a type left from the quarks and squarks, 3 generations of a type right from the quarks and squarks, and I don't care about non-type guys. If you want to construct a complete model, then you care. But for the purpose of the example, I'm fine with these guys there. So this is the matter sector, and for the gauge sector, I will just take this through QCD, and I have here a Guarino field and a blue one. So this is the fields lying in my theory, and what I want this theory to be gauge invariant under QCD and supersymmetric. And by assuming these 2 things there, I can write down the Lagrangian, and this is the result. The Lagrangian is quite compact. So the first line you can recognize, this is the field strength tensor of the gluon squared. This is a Dirac Lagrangian for the Guarino. Those are the Klein-Gordon Lagrangian for the squarks, and the Dirac Lagrangian for the quarks. But those guys must be massive. So here I'm just opening a parenthesis that will be closed in 2 minutes. I've asked the supersymmetric theory that when you add masses for the quarks and the squark, and the Guarino, you are breaking supersymmetry. But I need to break it, because otherwise I would have already observed the particles today. If supersymmetry is exact, then we should have a scalar electron of 511 keV. This couldn't have escaped detection. So we need to break supersymmetry. I don't want to tell you how. The result is that we have mass terms for those guys. And the mass of the squarks and the quarks are different, and the mass of the Guarino is different from the one of the Guarino. So this line is breaking supersymmetry. So that now I'm closing the parenthesis. And I have those additional terms here, because if I want to write down a SUSY Lagrangian, a supersymmetric Lagrangian, the first line is not enough. I need to add this extra piece. If I'm applying the SUSY transformation to all of those terms, except the mass terms, the Lagrangian is invariant. So I really need those guys. And this is 4 scalar. Here I have 4 scalars interactions here, and this is Guarino quark interactions. Kind of. Non-gauge interactions. So this is what I have to implement in practice. So now how to start my finals model right from scratch? That's the question you're probably asking to yourself now. And this is the answer. So first of all, the syntax is a mathematical syntax. If you try something else, finals will crash, of course. And what is a finals model file? It's just a text file with a .fr extension. And this text file is divided in 5 sections. The first one is a section that contains information about the author, the model, and it defines all the indices which will appear in your theory. So here, from that Lagrangian, you can see already that we have a gauge index here, this A. We have this I, which is just a generation index, and hidden there is a color index for the quarks and sparks. So we have 3 indices here. Those must be defined here. Author and model information are important in the sense if someone is using your model, he might want to contact you at some point. So it's good to give him information. So this is the first part. The second part is associated to the definition of the gauge group. And how to define a gauge group, you need to say if it's a Abelian group or not. You need to provide some representation matrices which will be used to construct the cobion derivatives. The structure constants of your gauge group, if it's Abelian, of course. What's the coupling constant? That's important. And what's the associated gauge boson? And sometimes, if you want to use superfits, you just associate it supervector superfit, not the gauge was. So that's for the gauge group. When this is defined, you can start defining all the particles of your model. And what's the definition of a particle? It's just to say I have a particle which has that name, that spin, this PKG ID, which carries this and that indices, and then I do some options like is it side conjugate or not? What are the quantum numbers of that guy? What is his mass? What is his width? And a nice features in finals, which in fact is a nice features of finance which we have stolen, is that you can group similar particles into classes. That means you don't have to implement an up quark, a top quark, and a chunk quark. You can implement a quark and saying that this quark is appearing 3 times. One for the up, one for the chunk, and one for the top. So that's avoid redundancies. So the fourth part consists of the parameters of your model, and finally you need the Lagrange. And so this is your final model file. So now let's do that for SUSY. So this is the preamble of the model file. So this is this third part, this first part, with the author and model information and the definitions of the indices. So first of all, you need to give a name to your model. And I'm very original here, I know. It's a SUSY QCD theory, so my model is called SUSY QCD. But you can write whatever you want here. If you want to call your model banana, you can. It's just a name. But then this name is propagated. So if you want to spread out the model in the community, beware. Do not use too fancy stuff here. Otherwise people will laugh. Okay, you know what's going to happen. So then in this second chart here, add information, it's information about the author of the model. And that's important, as I was saying before, for other people which are using your model to be able to trace you and to ask you questions if they have some. And this is my name, this is the date of yesterday. Okay. This is the first version of SUSY QCD, and this is some way to contact me, my email address and my institution. And I can also add some references. If I'm taking the model from a paper, I can give the reference of the paper. Or if I'm writing a paper associated to the model, I can give the reference of my own paper. And also, at the end of the game, if the model is really well validated, we are offering users the possibility to upload their model to the Finals webpage. I haven't put the link to the webpage here, it's my mistake. But probably, I guess it's on the wiki, right? The link to Finals? If it's not, I will put it in a month after this lecture. And so we can open a web page on the Finals wiki with your model, and you can put the model files, the validation units, everything. So any user, first of all, the user can download your model from our web page, and second of all, there are many information that are also left on, and what should be done next. So this is for the first part of the preamble, author and model information. What about the indices? In our theory, we have 3 kinds of indices. The gluon index, the color index of the quarks and sparks, and the generation index. So what is the definition of an index? Just saying, I have an index called gluon, and this index is going from 1 to 8. I have an index called color, and this index is going from 1 to 3. And I have an index called gen, for generation, and this index is going to 3. Several remarks are in order here. First of all, I have this no import type here. Because when I will expand my Lagrangian, I don't need to replace each term containing a quark by one term for the green quark, one term for the blue quark, and one term for the red quark. I need to keep one term, the color implicit. That's the purpose of this no import.
You can add as many ones you can, or
here?
Yeah.
As many as you want. You just need to use different names. And for the generation index, it's just a regular index going from 1 to 3. For the names, you can choose whatever you want, except for gluon and color. Those are reserved names. And the reason is very simple to understand. QCD is a very special role at colliders, at the LHC, and also in Monte Carlo tools. The running on alpha S and etc. etc. So finals must be able to uniquely identify what is QCD. And the way to do that is to have a reserved name for the QCD indices, the chart one and the fundamental one. And also, we have a reserved name for the coping constants here, GS and alpha S. For the fundamental color matrices, which are denoted by T. And for the structure constants, which are denoted by N. So QCD, you have not that many freedom, because QCD has a special rule. But for the rest, you can do whatever you want. And finally, associated to those index, you can associate an index type or a letter. What does that mean? Does that mean that any color index that Findable should create will start with an N? Any gluon index that Findable should create will start with an A. And you can write any letter you want here. So this is just for readability. And this achieves the preamble of your model file. So now you can really start to implement your model itself. And let's start with the gauge group. So first of all a gauge group is often divided into several direct factors. And all those direct factors will come into a list, which is n gauge groups here. And one element of that list has this form. So this is how to implement SU3C. So this is a name, SU3C. Again, you can write whatever you want here. Upload, if you want. No problem. What is important is the types here. First of all, you can say if your gauge group is abelian or not. SU3 is non-abelian, so I will switch this slide to false. Very important, you need to associate a gauge boson to your gauge group. So G will be the letter of my gluon field. And this is a reserved keyword. But for a generic gauge group, you can put any field you want here. And also, this defines internally the index related to the adjoint representation of your gauge group. Because your gauge boson lies in the adjoint representation. So Findable will just say, okay, G is the gauge boson of SU3C. So let's see what indices carries these guys. And this guy carries an index called gluon. So gluon is the adjoint index. So this is very important to associate a gauge boson to a gauge group. If you don't want, you can have a superfit here. But I will come back to that later. So for the moment, just use a gauge boson here. Then you need to associate the coupling constant, the structure constant, and some representation matrices. So for QCD, you have to do that. For other group, you can choose whatever you want. And for, of course, abelian group, you don't have any structure constant representation. Then you have a U1 charge. For more information, I will always refer to the Findable's manual, of course. So this is downloadable from the wiki. So just go to the wiki and download it if you are interested. And one remark here in this representation tag, we link the index name color to the T matrices. So in representation here, we'll always link a representation matrix, a symbol for a representation matrix, to a given index. And since Findable knows the range of your index, he knows also the dimension of your representation. And by doing this, automatically, Findable will construct for you nice tools to write down Lagrangian. The first of these tools is the field strength tensor. This column, Fs G mu nu A, is just a field strength tensor of your gluon. So you don't have to write down d mu G mu A minus d mu G mu E plus blah blah blah. You can just write down this much shorter. And the same for the covariant derivatives. You can use DC symbol acting on a field. This is on Lorentz index here mu, and this is the covariant derivative of your field with respect to QCD. So this is automatically defined. So you don't have to write down all the terms. And if your gauge group is complicated, for instance, like SU3 times SU2 times SU2 times U1, because this is large, these covariant derivatives automatically have all the terms.
Yeah, you do only unitary group, in fact.
Sorry?
You don't specify what is the group, except the weight of the color. So you presuppose that all groups are a unitary group.
Yeah.
Is this a real restriction or what? They're not for physics.
Probably yes. Because I think the representation matrices are assumed initially. I have to check internally, but I think that yes. I think. So this is for the gauge group. So here we have introduced a gluon. But let's start to code or to implement our particles, and let's start with this gluon. This is how to declare a gluon. So first of all, there's a M classes description tag, which is a list of all the particles of your model. And one element of it is something like this. And this defines a particle. So let's look to this together. So first here, there's something denoted V1. So V stands for vector field. So this letter here is very important. V is a vector field, S is a scalar field, F is a Fermi field, etc. And this number here must be different for anything, but you can write on anything you want. If you want to start with 9,900,000 whatever, you could. No problem. You just need to use different ones. So then you define a particle by its class name, which is G. So this is the symbol of your particle, which could be used in your Lagrangian. And for the rest, those are options. For instance, my particle is self-conjugate, so this is true. The index is carried by my gluon, the gluon index. I want to have a massless particle without any width, so I could do 2 times to 0. And finally, the PTG code of my particle is 21. There are many, many other options I could use. Some of them are here. For instance, in physical definitions, if I want to have an unphysical particle, I could. So I can just write unphysical is true. But then I need to provide a definition of my particle in terms of physical ones. Because at the end of the game, my Lagrangian can only contain physical states. I don't want you don't want to simulate things for non-existing guys, right? In the standard model, we have the B field, the U1 hypercharge field, and this one is not the physical one. The physical one is the photon and the Z. So you could use B and WI to construct our Lagrangian, but at the end of the game, we need to rotate to get the physical text. And this is possible thanks to this. I'll show you another example tomorrow. And then you can specify the name of the particles, give some quantum numbers to your particles, or I will just refer you to the manual for all the possible options. So this is some of them. And this defines my gluon. So now we can go, so this is the gluon, the next component of my vector multiplet is the gluino. This is how to define the gluino. You can see that it's exactly the same, I have the same tags here. I will just have an F here for fermion, because I want to use a 4th component fermion. So F is a 4 component. I'm insisting on the 4 component. I will come back to that in a moment. So those are the regular Dirac and Majorana fermions for those who don't know. So the class name of my guys is GO. And for the fermion, this will automatically create a symbol for the gluino, GO, but also a symbol for this symbol GO bar, which is if I have a fermion psi, the psi bar is psi dagger gamma 0. The 0 gamma matrix. So this is the symbol for the psi bar. So you don't need to really to define this one as well. So you have the 2 or 3. And so finally the gluino is a Majorana guy, so it's a conjugate, it carries some index, some gluon index. This is its PDG ID, 1,000,021, and this is the mass and the width. So some remarks here in order. So first of all, when you give a non-zero mass to a particle, you can associate a numerical value to this mass. And in fact, you have to. You need to provide a numerical value for the mass. And here I've chosen randomly 500 GeV. But sometimes your mass is just a formula. You can express a mass in terms of other parameters of your theory. So here we just say that you will just replace 500 by internal. And when you will declare the parameter, you will just put the mass there with the correct formula. So you can use the formula if you want. Otherwise, you can just put a number. For the width, it's the same story. Here I've chosen 10 GeV. This is, of course, wrong. If you take your model and compute exactly the width of the gluino, you will see that it's not 10 GeV. But here it's an example, so I don't care. I just put 10 GeV. But when you're choosing the mass and the width of your model, you need to be careful that the value here is really consistent. You cannot do whatever you want. Right? Yes?
Is there a provision, to calculate the decay of flight timing?
Sorry?
Let's say this particle is not standard model.
Yeah.
And not discovered particle. So then, is there a way to calculate the decay from its allowed decay modes and then put it back?
I mean, automatically,
Or
you'll
maybe
take,
on flight here.
today I will answer no. In 3 months, I will probably answer soon. And in 5 months, I will answer yes. So it's in the order.
But then I have a question. Then let's say I'm doing this symmetric theory.
Yeah.
And then I have to know the decay by some means, right? Because if I put in some dummy decay by hand.
Yeah, but I mean, what you are doing now is just you take a model file, you just remove all the decay width, or they are not there. Finals calculate all the possible decays. Using Finals FunCalc, calculating analytically the decay partially, summing them, and then you get the number at the end. And so you can reinject your numbers. So this is not the full story, of course, but this is already something which is more reasonable than putting something randomly here. If you take any spectrum, for instance, if you take SDK for the SUSY models, then you will have all your decays computed at one loop order, if you see it. But here, if you write on a new theory, in principle, you don't have such tools. So either you calculate everything by hand for your model file, and here, Panus will just compute for you all the possible decays. Like, let's say allowed decays, sum them and give you the number to put here. But this is not today. In 5 months, probably. Maybe more. Right. So this 10 GB is just some random number I choose. But if you really construct a model, be careful of the number you will put here. Because you cannot do whatever you want. So some parameters now. I'm talking about 4 component kernels here in this hack. So what kind of kernels do I have? In fact, I have 7 of them. And let's start with the poly matrices. I can construct the sigma mu matrices here. So this is the form of the sigma mu matrices. And if you, those are 6 2 times 2 matrices. And if you check, those matrices are fulfilling the Lorentz algebra expression. So that means those are a representation of the Lorentz algebra. And in fact, you can say it acts on some complex left-handed spinors psi alpha. So since those guys are 2-dimensional, 2 times 2 matrices, this guy is 2-dimensional, and this is a 1/2 zero representation for the kernels. And if you want to construct a Lorentz summation acting on this guy, this will be given by the exponentiation of the sigma mu matrices, where this omega is just the parameters of your transformation. And so this is a Weil kernel, a 2-component guy. You can do the same exercise with the sigma bar matrices here, and you will see that those guys are also fulfilling the Lorentz algebra. So this, in fact, defines the 0.5 representation of the Lorentz algebra, the right-handed phi spinors. And usually we are denoting them by chi bar alpha dot. So the alpha dot and alpha indices, dotted and undotted indices are conventions for a very practical one for left-handed and right-handed spinors. And of course, you can, from this sigma bar mu matrices, you can construct transformations here. So we have 2 types of spinors here, left-handed ones and right-handed ones. And there are 2 different representations of the Lorentz algebra. And to go from one to the other one, you can just use complex combinations. And one thing which is important, if you want to write on the Dirac mass terms, you need both. So you cannot use Weil representations to describe the quarks. You need both of them. You need one left-handed guy and one right-handed guy. And the mass term will mix those. So this is not practical. So in principle, we prefer to use Dirac's fields for the quarks and all the fermions. And this Dirac field just contains both a left-handed guy here and a right-handed Weil spinor here. So this is a 4-dimensional representation. And from the sigma mu matrices here, sigma mu and sigma bar mu, you can construct these gamma mu matrices, which have that form. I think in the literature, usually people are written this by S mu. And this matrix is also a representation of the Lorentz algebra, and this will act on those Dirac spinors. And if you write down the finite Lorentz transformation, you can see that it contains both the left-handed guy and the right-handed guy. So this is how to link Weil fermions to Dirac fermions. And finally, a Majorana fermion is just a Dirac fermion where this chi bar is just a psi bar. So there's a link between these 2 guys. And I was just saying that complex communication will allow it to go from left to right, and this is what is written here. Psi bar is just psi dagger in terms of Weil spinors. Right? And this epsilon, this rank 2 anti-symmetric tensor, allows to lower and raise indices in the spin space. So it's just a metric tensor in the spin space. Because this index is a factor index. So if you really want to do supersymmetric calculations, this indices is it's a nightmare. It's very important. But the message here in this parenthesis is that we have 4 types of fermions. We have 4 component guys, which can be a Dirac spinor or a Majorana spinor, or 2 component guys, which can be a left-handed Weil spinor or right-handed Weil spinor. And those guys maybe not the physical guys for quarks and atoms, but sometimes it's easier to write on the Lagrangian in terms of those quantities. So it might be good to be able to have those in finals, and then finals will automatically do this mapping of two-component guys to four-component guys. And this is possible. If you take Arduino here, you could have used the Y components options. Just to add it here. Y components is fixed to another particles, and this other particle would be a Y fermion. And how to declare a Y fermion? We just need a W instead of the F here. And then a Y can be left or right-handed, but that's a difference with respect to the Dirac and Majorana fermion. And how to link it? It's just to use Y components pointing to psi and chi bar for this guy here. Or for the Arduino, it's a Majorana, so we just need one guy. And here I've chosen to call it Go. The same as for the Arduino, but use a W at the end for Y. And I will show you a concrete example tomorrow how to use Y fermions. And this is very practical to write on Lagrangian. So maybe you can say it's useless. I will never say that. Y fermions are great if you want to do theoretical calculation. If you just want to do Fibonacci, probably Dirac fermions and Majorana fermions are enough. And this is the set of options which can be used for the fermion field. So it's the same as for the vector fields. And all of them are interconnected. You can do the same exercise for the quark fields. So again, it's the same story as before, with some differences. And the difference lies in the particle classes. So here, I've written the indices, and I've said that one of these indices is a flavor index, check. So if I will see this flavor index tag, he knows that, first of all, he knows that Chen is a three-dimensional index. So he knows that we have to create three copies of this guy. So UQ is the generic quark, and then we have class members here, and we have three copies of the quark: the up quark, the charm quark, and the top quark. So that allows to implement 1 times the quarks, not 3 times. And for the mass, width, and PDG, instead of having one value, we have a list. And one element of the list is linked to each of the class members. And for the mass, in addition, we have a generic mass of the quarks.
So what are the U mass? I mean, there are two.
Sorry? This is the generic mass for the quark. So this is a vector. And then each element of this vector, the first element is this one, the second one is this one, and the third one is this one. So if in my Lagrangian, I can use UQ and UQY, so these quantities, to write down a generic Lagrangian curve in family space. And when finally you pass this term to my graph, you just expand it into 3 terms. One for the up type quark, one for the up, one for the charm, one for the top. And if for the mass term, you will just say you replace mu by this big mu for the up, by this mc for the charm, and by this mt for the top. So mu is the generic one, and these 3 guys are the class members. Is it clear, or do you want to? Is it clear for everybody? So this class thing is very important, because that allows to implement things once instead of 3 or 4 or 6 times. We have 12 squads in the DMSSM. It might be good not to have to implement 12 things. Better 12 one. And here I've used the quantum number flag as well, just to assign the electric charge of the quarks. And this is important because then in the Lagrangian finals you check that all the quantum numbers are conserved. So if you write something crazy, or you are violating, for instance, the electric charge, finals will just tell you. And then you know that you might have made some mistake somewhere. So this is check. So this is the same exercise for the quarks. Now we just point you this letter here, which is S for scalar. And I won't enter into the details here. But the slides are available, so you can look to that carefully. Just download the slides and look at them. And so I have the left-handed quark here and the right-handed quarks there. And this achieves the fields declaration. So I will finish this lecture by the model parameters, because I think now I like to stop. So this is my Lagrangian. What are the 3 parameters of this Lagrangian? Of course, I have the masses here. But the masses are internally handled. As when I'm declaring a particle like this symbol is automatically declared as a new parameter. So I don't have to worry about the masses. Same thing for the width. The mass and the width is internally taken into account. So what are the other parameters here? Yeah, I've heard it from somewhere there. It's the coupling, GS. So I need to declare GS. And that's it. And in fact, that's not it. Because QCD has a very special role to play. So in fact, any single model you implement in Finance, if you want to export it to MGraph, you need both GS and AS or alpha S. These two guys must always be there because the information must be passed to MGraph in some way. So if GS and alpha S are not there at the Finance level, there's no way to pass them to MGraph. So you need to declare these two parameters there. And how to do that? This is the answer. So you have a list which is n parameters, and one element, in fact 2 elements of this list will be this. So AS here and GS here. What's the difference? This guy is an external parameter. This is a free parameter of my theory. I need to assign to it a numerical value, which is the value of alpha S at the Z-pole. This is a requirement. Alpha S must be given at the Z-pole, and then MGraph, we know that 0.1184 is the value of the Z-pole. And then you could do the running consistently. Then GS is not external, it's internal, because I can express GS in terms of alpha S, right? So I will say this guy is internal, and instead of writing a numerical value here, I will write on a formula. And that's it. That's the two types of parameters I can have. So now, what this interaction order thing? If you remember from yesterday, you had this coupling order in MGraph. QCD equal 2, QED equal 1. That's how Finance knows about the coupling orders. And that's how he knows how to give information to MGraph. What does that mean? Is that GS is QCD equal 1, and alpha S is QCD equal 2. So if you write on a vertex with alpha S, Finance knows that this vertex has a coupling order of QCD equal 2. If you write on a vertex with GS, Finance knows that this vertex has a coupling order of QCD equals 1. That's how Finance knows the information. And this additional type here, parameter name, is also a requirement because GS must be called G in MGraph. So when Finance will see a GS, before feeding MGraph is a GS, we will replace it by a G. Yes?
What I understood is that GS, QCD equal 2 means it will have two QCD vertices. If you take the Feynman diagram which involves two QCD vertices,
Yes?
then I don't understand this GS equal to, QCD alpha S, QCD equal to is actually GS.
Alpha S is GS squared, right?
Yeah, but then the topic is
Yeah, that's what this said. If you have that vertex, this is GS, right?
yeah.
So this is QCD equals 1, right?
Yeah.
So now if you have that vertex, you still
Oh, I
score.
understand. You are using the vertex
Until you can write it with that vertex. So this QCD equals 3, or GS squared. Okay? And this achieved the declaration of everything but the Lagrangian, and I think the Lagrangian will be for tomorrow, right? Or do I have more time? I don't know. Maybe no, there is stuff here.
So, do you have any questions?
Can you show me the last
This one?
Yeah.
This one I forgot to say that's the other options. So, it's
So is the order of external and internal information? I mean the channel.
Yes and no.
Declare GS first and
yes and no. The order among external internals, we don't care. What is important, here I'm using alpha S. So alpha S must be declared before GS.
before.
Yeah. But for instance, you can have a formula depending on other internal guys and external guys. So then the order is very important. You cannot use a parameter before declaring it. That's the restriction. Very good question. Other question?
Maybe this order is more convenient because I cannot tell the value of GS at MZ so easily.
Right.
Okay. Any other questions?
So can we modify the form of the propagator? For example, in the case of the auxiliary field or something like that, we can treat some fields which it does not propagate.
Well, in finals, the propagator are fixed. If you have a fermion, it will be a p slash plus n over square. But I know that people, I don't remember who, but someone is trying to modify the propagators using finals. Just to have a special list where you can define non-canonical propagator. So this, I know some people are working on this, but I don't know the status at all, because I'm not involved. And probably it will not be out before a year. Because we just released version 1.6. So we will not release another version.
So here I think you don't use auxiliary field.
Yes.
Then you are in unitary gauge and you have to fix the gauge before that. I mean, auxiliary field is needed in some ways and some gauge is not needed. So you have to fix the gauge and do the calculation.
Yeah, you can use auxiliary field, because you have this physical type here. Here. So you can define a field as a real one, as a physical one, and then you just say it's a physical force. So at the end of the game, it will be removed from the Lagrange and replaced by the definition. Okay. The goal is just to be able to write on the Lagrangian in the easiest way as possible. And then all the rotations, replacement, etc., mathematically do that for you. Mathematica has been done for pattern matching. Exactly this.
Yeah, I have a question. So the metric is plus, minus, 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 or and also the covariant derivative is
By default it's with a minus, but there's a tag can change to a plus. And this change consistently in the field strength as well.
I think that this model is just for standard model thing. It's very general.
The model I'm illustrating here is just a model I've chosen. But this is true for any model.
And you can also define some axial fields or...
Yeah, you can do whatever you want. This is just an example to illustrate all the features, and then you can apply this to your theory, to the theory you're going to be involved.
If the Lagrangian is correct form, if Lagrangian is correct
Yes.
form, then everything is possible. Everything.
Yeah. If your Lagrangian is wrong, then you can implement a wrong Lagrangian and do some great step at the end. But then I will show tomorrow there are routines to check that your Lagrangian is at least apparently correct. I will illustrate that tomorrow. You can check hermeticity, you can extract the mass spectrum and check that it's consistent. There are many checks you can do already at the finance level. It helps. Check quantum number conservations at all the vertices. But this is already a strong check.
Then, for instance, well, chiral perturbation Lagrangian unit.
Yeah.
The pion scattering.
Yeah.
It is possible to make.
I think, yeah, it is. And the models are available on the web. Yes? Those? The mass in the region, yeah. Those names, those symbols, those are I've chosen. Here? Because I've decided because the upward and jump out are without any risk. But if I let's say for the squawks, for instance, here, I have a width for all of the guys. The name I've chosen. You can write whatever you want here. If you want to call your width blah blah, you can write blah blah. No problem.
What is it from by default?
there's no default. The math, you need to fix it. Here you're saying that the mass of that particle will be associated with this symbol. You choose the symbol. The only keywords are for the gluon. Here. For the QCD, in fact. The gluon field must be called G. The strong copying constant will be called GS and alpha S, or AS, in fact, with a capital S. The fundamental correlations are G, and the circuit constants are F. All the rest, you're free. And also, at the end, this is color regular.
Okay, so if I invent, if there is a new model, then how can I assign the PDG ID for a new particle?
If it's completely new, it's not documented. If you're not giving any PDG ID, Pinus will give it one for you. And you start from 9 million and add 1 unit to each new. So if there's no PDG ID, the PDG ID is a good way to identify the particles at the Monte Carlo level as well. So if it's not there, just Pinus creates one from scratch, and you don't have to worry about it. But if it's existing, we do recommend to use the existing ones. Because to spread out your model in the community, I could, for my gluon here, I could write down, instead of 21, 6,066,066. Yeah? But then, okay, it's a gluon, everyone knows that the PDG ID of the gluon is 21, better to use what is existing. But if it's not existing, you can do whatever you want. There's no restriction on that.
Okay, probably once we start tutorial
Yeah.
of the mathematical program, probably will understand it. Okay, so let's have a coffee and let us come to lecture.
타임을 써봤어요?